All right, so in 5.2, we are talking about inverses. So I guess the first question is, what is an inverse? What does it mean to inverse something? Like in general, what does it mean to inverse something?
Perform the opposite.
I didn't catch that.
The opposite.
I would do the opposite, like to do the opposite or to undo something, right? Okay. In math, so we have a function, it's got an input and an output. And what an inverse does is it inverses the input and output of those things, right? Basically, F takes it one way, F inverse takes it the other way. So we talked a little bit about that if you watched the lecture. To do the inverse means to undo something. So we've talked about sort of like inverse operations. If you subtract and add versus if you multiply and divide, those would be sort of inverse operations. So we talked about what they look like numerically. We talked about what they look like symbolically. So there's going to be some swapping and solving. And then the next thing was what, one-to-one? And so what does one-to-one mean? That means your inverse is kind of like what? So a function goes one way. It's like if there is, we look for repeating x. And if it has a repeating x with different y values, it's not a function, right? So a function has a unique y for each x we input into it. So for every input, we get a unique output. What does one-to-one mean? Or what am I getting at here?
An inverse function has a unique x for every y.
Yeah, so a unique output for every input. It's like the opposite way of a function, right? We look at the y's and we see that there's no repeating y's. If we do that graphically, if we look for a function, it is the vertical line test. If we look for it to be one-to-one, we look at a like horizontal line test, right? Okay. So I think jumping into them, there's some good examples. If we open a window, how do I want to inverse opening a window?
Close it.
Close the window. If I'm climbing up a ladder, how do I inverse climbing up a ladder?
Climb down the ladder.
I climb down the ladder. If I'm walking into a classroom, sitting down, and opening a book. So now we're doing three things. How do I inverse these three things?
Close the book, get up, and walk out.
Yes. So we have to close the book first. We have to undo sitting down by getting up, and we have to undo walking in by walking out. So we have to do the opposite. And then if we have something in a sequential sort of order, we have to do it in a backwards sort of order, right?
Yeah.
Opening the door and turning on the lights. Guess how I'm going to undo that? I'm going to turn off the lights, and then I'm going to close the door next. Questions about this? So I know like we and I've talked about this in the lecture, but like we do this stuff in math, but like you can kind of generalize a lot of these sort of concepts, right? Math is sort of one of the first places that people really get introduced to sort of this deductive logic and sort of stuff that's happening here. That's basically what this is. Like this is an application of sort of logic. That's all math is an application of logic to numerical sets, basically. We talk about a set and we talk about a relation between the two things. That's about all we talk about in math. Just two things, that's it. But you can apply the set theory to other things, right? That's what they're kind of getting at here, I think. Okay, so I know we're not supposed to do all these. Which ones are we supposed to do? 53 and 55. And there are a few ways to do this, but the way I prefer to do it is to swap and then solve. Some people solve and then swap. Okay.
I swap and then solve too.
Okay, so I talked about it in the notes. If I were solving this, I would not write it as like f of x equals 3x minus 1. First thing I would do is get rid of this notation, to be honest. And so instead of f of x, what can I write here?
Y.
Yeah, so if you write y. I was thinking about something. I would have the hardest time saying like these sort of words. Rolled and rolled.
World and world.
Yeah. It's one of the like, I don't know, man. It's
Spam spelled different.
yeah, I was having a problem saying words. Is what it reminded me of.
So good.
Okay, so I talked about swapping. What am I swapping in here?
X and Y.
I'm swapping the x and y. Well, everywhere there's an x, I put a y. Everywhere there's a y, I'm going to put an x. Do that. And then what am I going to solve for? If I swap them, I'm solving for what variable?
X.
Woo!
No.
The other one. Yeah, y. So swap your x and y, solve for your y. That is the strategy to solving your inverse symbolically. I think this might be the hardest way we make you inverse something. Do it numerically is so simple. If you get that wrong, I don't know what to tell you, man. Like, ooh, that should be like a gimme. That should be some gimme points on this. If we give you like a table and tell you to solve the inverse.
Thanks for the heads up.
Yeah, it is easy. I didn't mean to like.
You're good.
Yeah. You literally just flip things. That's it. Graphically is a little bit difficult too, maybe. But not too bad. If you write out a
No.
table. You just gotta write out a table and just like take your time a little bit. Just graphs take time, basically. You gotta go graph something. Ooh, didn't put my phone on silent. I'm about to fix that. One more minute, but I think y'all should be just about done. Come on, phone. Be silent. Okay, so I want to swap my X and my Y. Here's my swap step. Once I swap them, that means this is now the inverse. But we don't want the inverse solved like in this manner, right? We want to solve it for our Y. So I swap my Y. F inverse over here, right?
Mm-hmm.
Okay. If I want to solve for Y,
Yeah,
I don't want to. Yeah, y'all should, like, at this point, you should know how to do this, I'm hoping.
Yeah.
We've done like first order solving for a single variable. We've done that a few times. This is just a linear function, but I'm going to add the 1 over. So this is x plus 1 equals what, 3y?
Yeah.
And hopefully you get what, 1/3 x plus 1/3. It's probably the best way to write that.
Mm-hmm.
It tells you your slope and your y-intercept. And so there's one extra little step I'm going to do. I'm going to convert my y and call it my f inverse equals 1/3 x plus 1/3. And so this is just sort of what the notation looks like, right? And I talked about it in the notes, but like this is not an exponent, right? Don't look at it as an exponent. As some people try to do crazy exponent things. It's not what what that means. It just means we're doing the opposite of what f is, right? Some people say 1 over f or something like that. That's wrong. Don't do that. All right, so same thing here. This is like my f function right in here. I want to swap my x and my y, so my y becomes an x. This looks like 2. If it's an x cube, it's going to become a y cube. This one might be a little more difficult. But now, like, this is, I made the swap. Now I am talking about my inverse. So I'm looking at this thing. How do I solve this equation?
Add the 5.
We want to add the 5. So this looks like what? X plus 5 equals 2y cubed.
Yeah.
I think the next step probably is to, I think the
Divide
next
2
step is,
across.
yeah, divide by 2. So I think that next step is probably obvious or more obvious than the next one. This next one might be a little bit difficult, maybe. We got a y cube. How do I do this? I don't know if we did anything like this before. This might be new.
Cube root?
We got to do a cube root. We've done things with square roots, but we got to take a cube root of both sides. This is what, y? If we take a cube root of y cubed, that will give us a single y. And now we got what, cube root of this thing? 1/2 x plus 5/2. When I take a cube root, do I have to do that plus or minus thing? Yeah, remember that? Maybe I'm just trying to confuse you more. That only comes up when you do even roots, I believe. Because when we cube things, if it has a negative, the negative stays there. If it's got a positive, it's going to stay there, right?
And I just also want to bring up, because I see this coming up, is the domain of this thing. If it's a cube root, the domain is always what?
Do you remember what it looks like graphically? That might help.
Mm-hmm.
The cube root.
Maybe it would help to think if it's a square root.
Yeah, if it's got a square root, it looks like that. If it's got a cube root, we can take cube roots of negative numbers, right? If we take cube root of negative numbers, the negative comes out. Like a negative, what, 8? minus 2 by minus 2. You get 3 2s out of that. So we can do cube roots of negative numbers. They're going to give us negative numbers. So the domain questions that we were asking?
Yeah, I just want to make sure that, I don't know that we actually asked them about the domain of a cube root, but I know we're going to ask them about the domain of a square root. So
Yeah. So domain of a cube root is going to be all real numbers, right? Is what we're doing, positives and negatives.
mhm.
Square root. I already said this. It's going to look like. I've talked about square roots. It's got to be what, greater than or equal to 0. And if you don't see the 2, it's still there. Okay. Okay, so 87 says find a formula for f of x, identify the domain and range of f
Something
inverse,
in there.
and verify the f and f inverse. F and f inverse are inverses. Okay. Whew. Well, it felt like I was saying inverse too many times at the end there. Okay, so find the inverse of this thing. I think that is manageable with what we've done. And you should know probably, you could probably find the domain and range of these things. So I'll give you a hint. X cubed minus 5 looks like this thing moved what, to the right 5? It's just like this shifted to the right. It's just the right or left shift, right? I think Roxwell doesn't even consider an inverse to exist unless it is a function, right?
You know, I don't like that though, because you can have an inverse that's not a function. I
Yeah.
always put the word in there because it bothers me for some reason.
Yeah, you can have inverse relations.
Mm-hmm. But yeah, you're right. When they ask that, does it have an inverse? They mean inverse function.
Yeah, not everyone does math the same. It's kind of weird. You just got to look at how they do it sometimes and adjust. Adapting is an important skill anyway.
Right.
Yep. It's a rapidly evolving world. So y equals cube root. First thing I'm going to do is drop the function notation. Just because I feel like working with single variables is a lot easier. You're less prone to mess up on them things. The first thing I want to do is, there's 2 things you got to remember, basically. It doesn't really matter what order you do them in. I just have my preference with doing what first. What am I going to do to this to find the inverse?
Switch your x and y.
And then,
Add the, well, no.
yeah, you got to
Did you
do
take
this.
the cube root?
Okay, this is a cube root. How do I undo a cube root?
Cube root both sides.
Not rooting. I gotta raise this to what?
Third power.
I gotta raise this to a third power. A cube root is the opposite of raising something to a third power. And I don't think we really got deep into like doing things with fractional powers. What if this is like x and I'm doing to the third? You can look at a cube root as like a 1/3 power. And this also fits like our exponent rules that we were looking at. If this is like a to the 1/3 power, multiplying it by 3 should get rid of it. Like 3/1 is the reciprocal. It should get rid of that 1/3 or that cube root power. I don't think we did this with the fraction.
I don't think so either.
Yeah, I think we skimmed over that.
Rational exponents is kind of an important concept, but that's okay.
Basically, if you're doing a cube root, right, we're looking for 3 of the same thing. It's by dividing by 3, kind of sort of in the exponent. Okay. So if this confuses you, ignore it, I guess. I don't know. But this is x. To undo a cube root, we want to cube things. And if we did that, we get rid of the cube root. This looks like y minus 5. So I like that you said that because like order is really important on this thing, right? We got to get rid of that cube root. It's sort of like there's like parentheses on things when you have them underneath a radical. And then the last thing, I think that's probably a little bit more obvious now that we cubed it. We got to add the 5 over to solve for the y. And so my inverse function looks like x cubed plus y. I didn't talk about it, but I guess they wanted to do the domain and range here. What's my domain and range on this thing? If you want to go back to this graph, what's my domain? And, oh, if I shift this graph to the right 5, how's that going to change my domain? Is it going to change my domain?
No.
No, it's still going to be all real numbers. What is my range on this thing? And I don't know if I said it, but what is my range on a cube root?
Negative.
How far down does it
Oh
go?
shit, my bad. No, wait.
So this is going down, right? It is going down super, super slow, but it's going down. It's the tortoise, right? It may not be the hare, but it's the tortoise. Keeps going and going.
Negative infinity to positive infinity.
Yeah, so all the real numbers here as well. So you can either say what, minus infinity to infinity, or you could give me like all real numbers is also good, same thing. If that's my domain and range there, what should my domain and range on my inverse be? It's a little silly here because it's the same. I wish it would have been a little bit different. Might have made more of a point. But I'm hoping you could grab it off of this thing. If I wanted my domain for this thing, for my inverse, where would I look over here? Maybe that's a good way to ask it. If I want my domain for my inverse, I'm looking at my
Range.
range over here. So I should look at the opposite. So my y is becoming my x is becoming my y. So my range and domain should swap. If I'm swapping my x and my y, I'm kind of swapping the domain and range of what I'm putting into my function. And so it's a little bit silly because they're the same here, but technically I'm like grabbing this one from this one and this one from this one, right? Questions about this guy? It's domain range. The other thing is we could graph this thing, right? If we want to graph this thing, let's graph it right quick all on this paper. It is a cube function and we raise it up 5. So quick graph of what this thing might look like. Really quick graph. It looks like a cube function. If I look at the domain of this thing and I look at the range of this thing, the domain, it goes all the way left, it goes all the way right, the range, it goes all the way down, it goes all the way up. So it's all real numbers here as well, right? So thinking about what these things look like graphically might also help. Well, domain and ranges. The other thing is when they ask for domain, what they really want is domain restrictions. And so since this is a cube root and not a square root, there's not really going to be anything that we restrict. We're not dividing anything, so there's nothing that should be restricted with division. So those are the things you really got to kind of look out here. 87.101. Use the table for f of x to find the table f inverse of x. Identify the domain and ranges of f and f inverse. Ooh. This domain and range might be a little different than what we've been doing, so it might be good to go over this. Okay. I want to make up the table. How do I make up the table? What numbers are going in my x right here?
The y values.
I'm putting in the y values from the top one. 0, 4, and 16. And if I put in those values, what am I putting in these values?
The x values from the other
The x,
table.
yep, the x values 0, 2, and 4. So I'm swapping my x and y values. Make sure you keep the right x with the right y, right? Maybe don't just start shuffling things all around. But like that's all you got to do is you got to swap the two values. Okay, so if I want to talk about the domain and range, if I'm looking at my domain on my f, what is my domain here? Do you remember how to write these things? These are just single points, right? So this, we typically do things with like intervals, right? But this one, we want just single points. You should be using your set brackets, or the braces is what they call them, huh? And what is my domain here in my original function?
Domain for the original function would be 0 to 4.
0, 2, and 4. Just those single numbers. Are the numbers. Just those three numbers. I think it's kind of silly that it just says a singleton set when it's just a square function. But that's the way it is in the table. I think that's what they meant. I didn't look at the solutions, to be honest. Okay. If I have my domain and range on that f function, how quick do you think you can give me the domain and range on your inverse? I hope it takes like 3 seconds. What am I doing?
Just switch them out.
Switch them out. So this goes 0, 4, 16. Now my domain here, and 0, 2, and 4. It should be equal. Okay. Okay. We're doing 105 and 109, I think, are the ones that are. Oh, these are. We can do all these right quick. If I want f inverse of 3, how do I find f inverse of 3? So this is f of x. This is g of x. We have two different tables, so that might be worth noting. This is my f table. So if I want my f inverse, I hope you're only looking at this table. If I want my g inverse, I hope you're only looking at this table. What? What is 108 supposed to mean? You see that? I'm not sure what. Is that supposed to be inverse? Beats me.
Now, what is it? Which one?
It says g to the 21st of 0. I don't know.
I bet that's supposed to be an inverse.
I just figured you just copy and pasted these things. Did you like
I
write them
did.
down?
I did just copy and paste. I
that's
did
from the
not do
book?
that 21.
Is that from the book or what?
That
Did
is. Yeah,
did
I
it
just,
it's a
I
typo?
definitely just copied and pasted that. So,
Yeah, it's just a typo in the book, I guess.
yeah.
Huh?
Yeah.
All right. All right, so I want to do this. How do I find an f inverse of 3? What am I doing to find f inverse? So they're not giving us the inverse table, but this input to my inverse should be what quantity? Is it an x or a y value?
Y value.
We're inputting a y value to get an x. We're going backwards with the inverse. So I want to know a y value of 3. So where do you see a y value of 3 in the table?
Second column.
Right
X
here.
equals 1.
Yep. And so this should be equal to 1. I want you to find the next one, and the next one, and the next one, and we're going to do 109 as well. So for 109, I wouldn't write it like this. I would write it out with this definition. So hopefully you remember the definition. F of g f of g inverse of 1 is f of g inverse of 1. So hopefully you remember that definition. That's coming back from previous things. All right, so what do we got? 1, 2, 3, 4 of them to do. All right, I'll give you all a minute just to think about this, I think. All right, so what am I getting? Am I on mute still? No, I'm okay. Okay, so what am I getting for f inverse of 5?
Two.
Should be the number 2. We're looking along here where our y is 5 and we're looking at the x value of 2. G inverse of what? Minus 4. Sorry, G inverse of 4. I don't know, I'm saying minus. What number are you getting for that?
Is it 3?
It is definitely 3. We're looking along here where my y value is 4. I'm going to get a 3. So I think the most common thing people will do is they will try to do g of 4 or something like that. They will look here at the 4 and give me 5 instead, right? Go the inverse way. Start with your y and go back to your x if it's giving you an inverse. If you want to write out a table, we could completely just write out a table for this thing too, right? We just did a table on a previous problem. If you want to write out a whole nother table, if this really confuses you going backwards, you can do that as well. That is an option. You can flip them and write out another table for the inverse. I'm trying to streamline it a little bit maybe. If I want to do g inverse of 0, I'm looking at the 0. What is that giving me?
-1.
That's giving me the -1. I don't think there's a lot of ways to maybe mess that one up. There's only 1 0 on that table. Okay. If I'm looking here at 109, what is the first thing you see on the inside there? What is the first thing we should be doing? What's the first thing we're plugging in?
Find G inverse of 1.
We're finding G inverse of 1. So if we go to our G inverse table or G table and we do the inverse of 1, what is the inverse of 1 giving us? Oh man, even if you do this one wrong, you get it right. Broke clock's right twice a day, I guess. Huh? It is giving me 2. So I'm going to put in 2 and place in my G inverse 1. Those two things are the same thing. I grabbed it from the table. Now I'm looking at no longer. So hopefully you're not looking at your G table anymore. We are doing F. All right, so don't forget things you used to know. Just because we started doing inverses. This is still going F of 2. So F of 2 is going to give me what number?
4.
Oh no. Which direction am I going now?
Five.
Should give you 5. I'm glad you said 4. Okay, so I want to go back over this. When we do inverses, we go from y to x, right? We're going from 1 to 2. And so for g inverse of 1, I can put 2. But now when I'm doing just f of 2, I want to go the original direction like we've been going. So I'm plugging in now. This is an x quantity of 2. So now I'm looking along here for my x's for an x quantity of 2, and I see it here, hopefully. Okay, so 121, the graph of f computes the balance in a savings account after x years. Estimate each expression. Interpret where f inverse of x computes. Interpret what f of x and f inverse of x computes. Ooh, get a little closer on this, maybe. focus. That's not a whole lot better, but it's there. It might be a little better than it was. F of 1, what is f of 1 giving me? So now, same thing, we have to remember, are we doing the original function or are we doing the inverse? So this is like we've been doing, f of 1. That 1 represents what sort of quantity, an x or a y?
Y value?
In the 1?
Oh, sorry, my bad, X.
If we're doing f of 1, we're inputting an x and we're getting a y out. We've been doing. If we want to look for 1 on our x, I guess there's not a lot of ways to probably mess this one up and do it the other way around. They are different numbers, definitely, right? F of 1 is giving me, it looks like the number 110. And so this looks like some sort of a balance in account. We have X is the number of years. Y looks like probably the cumulative balance. So it looks like after 1 year, we're going to have what, $110? All right, so B and C. This 110, is that an X or a Y value?
Why?
That is the Y value. So it's kind of obvious in this problem, right? It's not going to be an X value, hopefully. It's like 110. It's not even anywhere on our X axis. I want you to find these two things from the graph. The first one should be pretty quick. The next one, you might have to look for a few seconds, try to squint, shove your face towards the screen, squint your eyeballs. I guess you could also just print it out on your own paper. That probably would be way easier or something, right? Or bring it up on your own computer with the PDFs. All right, so f inverse of 110, what number is that giving me from the graph?
One?
It is giving me 1. If I plug in 1 to my f, I'm going to get 110. If I plug 110 into my inverse, guess what it gives me back? It's going to give me back 1. So these two should match up, right? This is quantity. It's the same point they're talking about, just in a different way. F inverse of 160, what number is that giving me when I look across here?
5.
It should be giving me 5. And I think they want us to interpret what F inverse of X computes. So what are we inputting?
Dollar amount?
We're inputting a dollar amount to get a
Year.
year amount. So given a dollar amount, F inverse gives the number of years to get there, right? Something along those lines. Or input a dollar amount, it's going to output the number of years. Okay. Are there any questions over anything we've gone over? Anything at all? Oh, it says it right here. Balance in a savings account after X years. I don't know how to read properly, apparently. But there it is. use the graph to evaluate the expressions. We did this in the previous graph. It was really easy to distinguish your x from your y in that previous graph. This one, maybe not so much. Get in a little bit closer. But we want to do these 4 quantities, and then there's one that's a composition of functions. Oh no, but you should know what those definitions mean. Write out your definition, and I think you'll be all right. You'll probably get it eventually. Sometimes it takes a few turns. All right, so if you see f of 4, f inverse of 0, f inverse of 6, f of f inverse of 4 is what those things say. If you see f of 4, what does this 4 represent? Is that an x or y value?
X.
That is an x value. Oh, that's going to matter a lot here. If we do f of 4, what is this thing giving me back?
Four.
It is giving me back 4. You can think about this as your x and this is your y if you wanted to. I have the point 4, comma 4 on my graph. It's another way to think about this. If I want the f inverse of 0, where am I looking at? What does this 0 represent now?
Y value.
That is my y value. So if I want to look at my y values, I'm looking along here. If I'm looking along here, this one's also going to matter a whole lot. What is my correlating x going to be?
0.
It is 0. That would be the point y and x. You got to make sure that that one's your y and that one's your x here. All right. And then the next thing says what? F inverse of what? 6. What is my f inverse of 6 here? So my 6 represents what value now?
Y.
It represents my y value. So if I'm looking at my y values, don't look at that axis, look at this one. I'm looking at 6. What is this going to give me when I follow it along? This is going 2, 4, 6, 8. This last one should be 10. So it's giving me the number. I already said it, right? 10. It's coming along there and looking at this thing here. Then I can say that my x and this is my y. I should have the point 10, comma 6 on my graph. Is what that represents. And this one, f of f inverse of 4. If we're looking at this thing, the first thing I see on the inside is f inverse of 4. And so if I'm looking back at this graph, f inverse of 4 is going to give me 4. What is f inverse of 4 giving me? Even if you get this one wrong, you get it right, I guess. Huh? 4. 4 is the point on my graph. And now if I go back, f of f4, it's going to give me 4. Also, without even looking at the graph, do you think you could do this one without even looking at the graph? And I think it said to check whether something was an inverse earlier, and we didn't, did we? I think I skipped over that instruction. What do we know if we compose like the f and the f inverse function? And what if I give you f inverse of 20? What is that going to give you? Or f inverse of f of, I don't know, 37? What is this going to give me? Is that a weird question?
It wouldn't give anything on this graph.
Just not on this graph, just in general.
Hmm.
If we plug in 20 to an inverse, or maybe this one might be the easier way to say it, right? If we plug in a 37 to a function, and then we inverse that function, what is it going to do with this 37?
Give it back.
It's going to give it back. It's going to give you the 37 right back to you. If we do it this way, or if we swap them, right? This should also give me the same thing back. This was our like definition of a function, right? F of f inverse of x is equal to x, and f inverse of f of x. So if we want to check if something is a function, these were the two sort of checks that we need to check. Two sort of rules we need to check. And I think we were supposed to do that on 87 earlier, right? With this one. And I think I skipped it. Okay. I want to do it one way. What I want to check, right? If I go back to 87 and what we were saying, what is that going to give me? My f of x function? It's on the inside. If I do something like cube root of x minus 5, and I plug it into my inverse function, my inverse function was x cubed plus 5. So I'm taking this thing and I'm plugging this entire thing into a cube plus 5. And so if I do a little bit of simplifying, what should I get out of this thing? If they are inverses, what should I be looking for?
Just the x.
I should be looking to get an x out of this thing. So I'm checking whether this thing is a property is what I'm doing. If I do f inverse of f of x, this is going to give me what? X minus 5 plus 5. I'm going to get the thing that I plugged in back out. It's going to inverse what I was doing in the first place. So I did it one way. We should really do it both ways. I should also check f of f inverse of x. It should work both ways. So x cubed plus 5. I do a cube root of what? X cubed plus 5 minus 5. So either way you do it, you should be getting x. So if we want to check whether something is an inverse, we have to plug one into the other, or plug an x into the composition of both of them, basically, and see if we get an x back out. We want it to undo whatever we did to this x, right? If it undoes whatever it does to the x, we're going to get the x back out. This is basically what this is saying. Plug the x in, it does something, it's going to undo it. Getting close. I need to get those. I think that was the last one in there. So now we're going to that the concept of one-to-one functions. Zone out a little bit. We want to check graphically whether something is one-to-one. So if it is a function, let's check whether this is a function. Is this a function? And how do you know?
It is a function, vertical line test.
We're looking at a vertical line test. It looks like this might be questionable in here, but it is still going up throughout that thing, is what I would say. It looks like it, but if we zoom in, I bet it doesn't look quite like that. I bet we could see it's going through. It doesn't ever flatten up and down, right? Is what we're saying. Is this one-to-one? And how do we check if it's one-to-one?
Horizontal line test.
We do a horizontal line test. Is this ever going to hit it at more than 1 point?
No.
So is it one-to-one?
Yes.
Does it have an inverse? Is its inverse a function is what the book really kind of means.
Yes.
Yes. If you say yes to one, guess what? You should say yes to both of them. That means the same thing, basically. If your inverse is a function, it is one-to-one. If you have a function and its inverse is both a function, it means one-to-one. And I mentioned this, but like something that breaks a function from a domain range. Y2 maybe. This is not a function. Range here. My inverse not a function. Having like two different x's going to a y, right? And this would be your inverse is not a function. So this would be my f is not a function. This would be like my inverse is not a function. So these are the thing that breaks it when we have one going to two, or we have two that goes to one, sort of thing happening, right? And so what we're setting up is like this sort of unique pairing. There's one y, and between every y there is only one x. So these things are matched up in a one-to-one sort of fashion, right? That's how I'm trying to think of other words to explain it. But there's one here, and it goes to one, and this one goes to this one, right? We're not duplicating either our results or our inputs, right? So hopefully that brings a little bit of context into why they're calling these things one-to-one. Okay, so we didn't do this graph. Is this thing one-to-one? Is it a function? Is the original thing a function?
No.
Why say no? We're doing vertical line test to see if it's a function.
My bad. Thinking of the other way around.
Yes, it is a function. I'm going to ask it over here. Function. Is it one-to-one? That is the thing that you should say. This one is absolutely what?
Not 1-to-1.
Definitely not 1-to-1. You get so many points that it's going to hit if we put a horizontal line across this thing, right? So many times. Infinitesimally, probably, because it's going up and down. Is its inverse a function? Does it have an inverse? It's the way the book likes to write it. I don't like the way the book thinks about things. If it's not 1-to-1, then
No.
no. The table is a complete representation of f. Use the table to determine if f is 1-to-1 and has an inverse. So these things are the same question. I'm going to be asking them as two different questions. Is it 1-to-1? If we look at the first one, I want to look at these tables right quick. Are these things functions, first off? If we look at the x's, do we see any like repeating x's? That's the thing that you're asking yourself. I think they are all different x values. So this is 1, 2, 3, 4. This should be a function, right? This should be a function. This should be a function. We don't have any repeating x values. Okay. So right quick, I'm hoping this doesn't take you too long to figure out if this thing is 1-to-1. Is this first one 1-to-1, and how do you know? What are we looking for?
Repeating y values.
Repeating y values. So if it has a repeating y value, is it 1-to-1?
No.
That makes it not 1-to-1. That is the thing that breaks it. Is the next one 1-to-1? 4, 2, 0, minus 2. Are any of those repeating?
No, they don't repeat.
They don't repeat. Is it inverse a function? Is it 1-to-1?
Yes.
Yeah. Is it 1-to-1?
And yes.
Yes. There are no repeating y values. All right, so it's just like we're looking at a function from the other way, right? We look for repeating y values instead of repeating x values now. Questions about what these things look like on a table? What they look like graphically, we do a horizontal line test. What they look like on a table is we look for the repeating y values. Determine if it's 1-to-1. What does the graph of this thing look like? Like, what is the basic sort of shape of this graph?
A V.
It looks like a V. It is a absolute value. And it's shifted to the right one, so I guess I'm going to do that. Is that 1-to-1? And how do you tell? What am I doing?
Horizontal line test.
Horizontal line test. If I do a horizontal line, is it going to hit it more than once at any point in there?
Yes.
It is definitely going to hit it more than once. Is it 1-to-1? No. Okay. The test is coming up positive, which means it's negative. Okay. So I guess you got to remember what direction that goes in, maybe. It's like more than one? No, it's not. Oh, it tells you right there, apply horizontal line test. How lame is that? Okay. Decide if the situation could be modeled by a one-to-one function. These might make you think for a second. The distance between a ground and a person who is riding on a Ferris wheel. The cumulative number of AIDS cases from 1980 to 2010 and the US population from 1980 to 2010. Okay. So what is the thing that breaks it being one-to-one? It's if your what does what? Y value does what?
Repeats.
Repeats. So if we think about this thing, what is our Y value on this thing? X is the number of seconds. Y is going to be, this is a really silly way to say height, right? This is between the ground and the person. The height of the person on the Ferris wheel. If the Y is the height of the person on the Ferris wheel, is that going to repeat?
Yes.
It's going to definitely repeat. They're going to go up, they're going to come down, they're going to hit the height twice. What we're saying is that Y repeats. Does that mean that it's one-to-one or not one-to-one?
Not one-to-one.
Not one-to-one. And 40 says the cumulative number of AIDS cases from 1980 to 2010. If they're doing cumulative, is your Y value going to repeat? Cumulative means like the total number, right? We're just going to keep on adding and adding.
The Y value won't repeat on that.
It's just going to go up and up, right? If they're doing cumulative. What about the US population? There are some people, there are new people dying every day. There are new people being born every day, right? Oh, man. I used to work with an older lady. Always just used to open up the obituaries and just laugh, saying there's new people dying every day.
I would say no on that one, but it could also be yes. It depends on the population.
They're talking about the US population. It's just gonna go up and up.
Okay.
If it's just gonna go
What
up and
if,
up.
what if so many people died from COVID that maybe next
There-
year didn't go up?
It's still gonna go up. I don't think enough people died. It didn't die. Like there's more people being born per year. And like the difference between the people dying and the people being born is large enough to where like I don't think COVID's gonna.
Yeah, I agree.
Um,
And what about if the AIDS cases between 1980 and 2010? What if one of those years there were no cases?
it's cumulative, so whew. No, because there would always be at least like one or two diagnosed.
Yeah, I guess so.
And per the year, there'd always be at least one or two. So per the year, it would go up, I would think.
Yeah,
I think they're trying to make it one-to-one.
I know. I think so too. I'm just being.
And the point is that it's going up and up. We're never going to have a repeating Y value, right? If we look at it on the graph, it should be really all be in the first quadrant, but it's probably going to be a graph that looks something like that going up. If we look at the US population, it should go up and up. I just looked at those numbers too, but they were from 2015. And then it was my other class. We had to figure out morbidity rates. And we just look at those numbers. I think, I want to say heart disease is around 600K. And COVID's around 200K. So I think cancer is right there at 200K, if I recall. I had to go back and look at the chart to be honest. Don't quote me on that one. But yeah, it is definitely up there. Like for a single disease, like it is not something to be taken lightly. I hope y'all don't. I hope you are taking it seriously. Like it is something that we have to do socially in a cooperative way, right? It's going to take everyone a little bit of effort to get rid of it. Okay. And even with that, like cancer was like, I'm pretty sure they're throwing in like every form of cancer just to get it up to like that, you know, this is just a single disease, you know, and it's like almost as much as cancer, I think. So there are several different forms of cancer, you know, so they're putting them all together in one bucket. But heart disease is also up there too, so I hope y'all are eating healthy and exercising. Okay, so checking symbolic skills, restricting the domain of fx so that f is 1-to-1. Okay, that is really horrible to write it out that way. This is a quadratic, so I'm probably going to want to swap things up a little bit. If I think about f of x, and I lead with the minus x squared into a plus 4, can you tell me what this graph is going to look like?
Inverse parabola.
So this is
And-
going to flip the parabola upside down, and this is going to I was going to ask, and this is going to
Move it up 4.
move it up 4 or raise it up 4. So it is flipped, and it is raised up 4. I'm thinking this is what my graph looks like. And they want us to restrict the domain so that it is at 1-to-1. So what is the problem when I'm doing this? If I'm doing a horizontal line test, it is that it is hitting it twice. Is there a way we can cut this thing? And where would you want to cut it on your x-axis to make it 1-to-1?
Cut it at the 0.
If we cut it along the 0. So if we cut it along here and we just like remove this part of it, right? And so our domain is going from 0 to infinity. And it even says like answers may vary. You could have went the other side. Another option is to cut it the other way and take off the right half, maybe minus infinity up to 0, maybe. But here they ask us to find the inverse. I gotta make sure I'm doing this correctly this way, I guess. So this is my y equals a minus x squared plus 4. I'm not a biggest fan of this problem. I don't really care for it too much, but it gets at maybe one of the points. Y equals minus x squared plus 4. If I want to solve for the inverse, I have to swap and solve. Y equals what? Minus y squared plus 4. If I do x minus 4 equals a minus y squared. And I have to multiply everything by a minus y plus 4 equals what? Y. Ooh, dropping my square. Here I should take what? Plus or minus the square root. If I'm doing the square root property, I should take plus or minus But I think I might end up dropping one of those if I go back and look at my graph. If I want to go back and look at the domain and range on, look at this one. On my 0 to infinity, when it's my domain, my range would be, looks like what? Everything from minus infinity up to 4.
Mhm.
And so this should match up with my domain and range afterwards. Because depending how you solve this, I think it's going to flip it maybe one way or the other. So if we go 0 to infinity in the domain, my range should be minus infinity to 4. Here, my domain and range should be flipped. So now my domain should be everything from minus infinity to 4. And my range should be everything from 0 to infinity. And so when we do the square root property, we typically take plus or minus the square root. But here, since we're only talking about, I believe, the positive square root, I don't think we need this negative here. I think we can drop the negative. We're only taking the positive side of this thing. And this is coming from the fact that we restricted the domain, basically. That's why we're able to sort of cancel out this negative part of the square root. And if we look at our range, it should be matching up with what we're saying. If we're looking at our domain, it should be matching up with what we're saying. We can plug anything up to what, 4 in here? If we plug in 5, it's going to start becoming negative in the square root. We can plug in negative numbers here. We're going to get a positive underneath the square root overall, right? We're going to put a negative on a negative. It's going to make it positive. We should be getting positives in the square root. Another way is we can do the domain restrictions. This has to be greater than or equal to 0 is another way to do this. Oh, I'm already over time. I didn't even notice that. If you got to go somewhere, I guess you got to go. But we could solve this for domain restrictions and they should match up. If we were to graph this thing, it looks like a what? Positive square root. I think it's going to go like something, flipping it about the y. So I think it's going to look something like maybe that in that direction. It's like a square root that got flipped, I think. I hope I'm drawing that right. Doing it kind of quick in my head. Okay. And what do we have left on? To B, we wanted to do 137 and 150. So we got 2 more left. We're going to finish these 2 up right quick. Graph y equals f of x and y equals x, then graph the inverse. All right, so how would you graph these things? It's probably the best way to start graphing this thing. This is what I would do, maybe. Make a table. If you wanted to make a table, what's probably the first value you're going to throw in your x?
0.
I would start here. What's the lowest value we can put in there? Probably throwing a 0 in there. That's not a bad one.
I see. -1.
I would start with the lowest value that you can put in there. So if you want to maybe graph a few things or a few points, I think 4 points would be pretty good. If we throw in a -1, I'm doing this right quick, -1 plus 1 is 0, and we're going to square 0, it's going to give me 0. I'm just throwing numbers into my function. Y'all should be able to do this hopefully at this point in the course. 1 squared is going to give me 1. If I plug in 1, it's going to give me 2 squared, it's going to give me 4. If I plug in 2, it's going to give me 3 squared, it's going to give me 9. We could also think about this as like graph transformation. So it is going to be a square root function. Grab my graph right up here. This is my original function, minus 1 there. 1. And we're starting and not going further left than this. We're starting here and we're only going greater than this number in the x direction. So this is my f of x here. I want to draw my y equals x. I don't want to spend a lot of time talking about that. To that angle. How do your f and your f inverse relate to your diagonal? Here's my f. Oh, I guess we'll do it. Let's see. 4, 1, 9, 2. So if I want to graph my inverse, I flip the points. I flip my f, and I flip my x, and I flip my y. If I graph my inverse, here we go. 0, -1 here. 1, comma 0, 4, comma 1, and 9, comma. Looking like this. How do those two things relate to that y equals x line? Well, what does it look like you're doing? Starting here. What do we call this? What's that property? Do they look similar somehow? How do those relate?
One's a square root and one's a square.
Yeah, but I'm talking about like with relation to this line. Like, how does it relate to the y equals x line? What are we doing? Do y'all see that? Is that a weird question?
Symmetric.
Yeah, it's symmetric, right? It's a reflection. Like if I flip it about this line, these two things are equal distance, right? This point becomes this point. Those two things are symmetric about the y equals x line. They're equal distance from there. You probably don't want to like just flip them like across that line. It's probably looks a little hard because it's diagonal. It's usually easier just to swap your points. Right? This is my x, this is my y, x and y, or my f of x. This is my f inverse of x. So I didn't label things properly. Maybe I'm going a little quick. But if I want my inverse, I'm swapping my points. If I do that, it's going to make them symmetric about the y equals x. If I want to do this last one, rise in sea level, is R a one-to-one function? The table represents a function R that models the expected rise in sea level in centimeters for the year T. This model assumes no changes in current trends. Is it one-to-one? What are we looking at to see if it's one-to-one?
On this one, it would be no repeating R values.
There are no repeating R values, so is it one-to-one?
Yes.
Use R of T to find the table of R inverse of T. But all we're doing is flipping it, so it should be 0. And so what does this do? If we put the what centimeters put centimeters of sea level rises, it's going to give back the year. Something along those lines, right? Tell me what you're inputting, tell me what you're outputting, and I think you'll probably get most credit for interpreting the thing, right? Basically, your output from the previous one is going to become your input and vice versa, right? We're swapping our input and our output. If you give me a sea level, I can give you the year that it was at sea level. All right, that's it. Any questions over anything?